I got my brief invitation. Can you come along and talk? And I want you to talk about where we are at gravitational waves and looking at the event horizon of a black hole. And I was thinking, gee, there's been a lot going on, hasn't there? So it's actually been a fun talk for me to put together, because I'm going to start off relatively slowly and then sort of pick up pace, pick up speed towards the end. But I think the idea of general relativity itself was first written down in its final form in 1915. And so 104 years ago, and I remember in about 2010, I remember I was at a conference in the States, and I was talking to Ray Weiss, who's one of the people who won the prize for the LIGO experiment. And he was telling me, if we're lucky, we'll have it ready by 2015. We'll be able, just a little bit worried that we might not quite get there. And so sure enough, 2015 rolls around, and the first detections of gravitational waves were made, were announced in 2016. And so the last 3 or 4 years have just been a kind of like an all-you-can-eat buffet, pretty much, for people who are interested in both black holes as astronomical objects, but also extreme physics. So as someone who's an astrophysicist who grew up wanting to be an astronomer, sort of somehow found themselves being a physicist, and has now kind of slowly been migrating their way back to astronomy for most of the last 25 years. This has really been a huge treat for me, and I'll talk a little bit in general, just to remind, I'm going to assume that not everybody here has seen black holes in a great deal of detail, and then towards the end we'll try and talk about what's really big. I actually had to check the web tonight to make sure that I was completely up to date. No, I'm serious. So we teach. So some of you will have been to the University of Auckland, and you'll know that we teach an introductory astronomy course. And so when I teach an introductory physics course, if you have a big kind of physics textbook, probably about half of that has been known for 200 years, and most of the rest of that has been known for close to 100 years if we're thinking about quantum mechanics. It's only right at the end. I mean, the stuff we're doing is super modern, but the basic rules of the game don't change very much. But if you're teaching astronomy, pretty much every time I teach it, there's something to read in the Herald or something online, something that sort of leads the public consciousness. That's going to change what it is that I want to say. I mean, this has never been more true in terms of our understanding of extreme gravitational events. So it's a very, very exciting time. All the fact that you're reading on a regular basis in a newspaper or whatever isn't a sign that maybe they just have trouble finding things to print. This is really something that's driving the field. So what I wanted to start by doing was well, some of you will have heard this before, but for those of you who haven't heard this before, the idea of black holes is a remarkably old one, and also actually a remarkably simple one to grasp in some ways. And so our story begins, it turns out there's no photo of this guy, our story begins with John Mitchell. He was, in fact, it was kind of a quiet period for Cambridge. It turns out it had about a 100-year lull where not very much of anything interesting happened there in the sciences, and he was pretty much in the middle of it. But he was at Queen's College at Cambridge, and he eventually went off to become a vicar. He was given what they call the living, in other words, the job of vicar and the income that came with it. And he had he did a huge range of things. He became kind of internet famous or Royal Society famous in the 1760s. He wrote this complicated analysis of this giant earthquake that had flattened Lisbon. The Cavendish balance, which was the first thing that people have used to actually determine how strong gravity is and to actually weigh the Earth, was something he developed. And he had a variety of friends. And so this sign here is on one of these blue plaques that's on the edge of the vicarage where he lived. And so in particular, he actually guesstimated the distance to stars. He looked at Saturn, and he said, well, if Saturn shines by reflecting the sun's light, and the average star, if we think the average star is about as bright as the sun, how far away does the star have to be in order to be as bright as we see it? He got within about a factor of 4 to the typical distance to the stars. So he's one of the first people who really, he changed in a variety of ways our understanding of the universe. But he also did a bunch of things that were completely ahead of their time. And one of the things he did was to come up in 1783 with the idea of what we would now call a black hole. And so the way that he did this is, firstly, he was both lucky, but also it turns out completely right. The formula that he wrote down for the size of a black hole, just by chance, the one you get from an understanding of Newtonian gravity, turns out to be exactly the same size as the one you would get from Einstein gravity. And what he did is he asked himself a question sort of like this. How many people have seen this video? This is Apollo 14, I think. It's Al Shepard. And he's playing golf on the moon. It's not the highest definition video. He's going to take a better whack at it in a second. He slices his first one. Then he has a do-over. Whack it. Well, the key thing here is that the moon's escape velocity, it turns out, is about 2.8 kilometres a second, so a reasonable amount less than the Earth. And a golf ball actually goes much, much slower than that, about 0.06 of a kilometre per second. So you can't whack it any harder on the moon, it's just that it will go further. And so the question that you can ask yourself is how hard would I have to whack a golf ball for it to go further away? How small would the moon have to be for the, for the golf ball to escape into space? And so the same question, or a slightly different question, is the one that Mitchell asked himself. He assumed that, or he believed that light consisted of a string of little particles, what they call corpuscles. Like little bullets that were fired from a hot surface was what he imagined light to be. And he assumed that gravity would slow those little bullets down if they were starting off from something particularly heavy. So what he asked himself is, how big would I need to make a star in order for its gravitational field to be so strong that a little bullet moving at what he knew to be the speed of light, which they'd been measured pretty accurately even back then, how big would the star need to be in order for its escape velocity to be greater than the speed of light? And that's a question that you can ask if you've done NCA 2 physics, maybe 3, certainly 3, you could ask this question, you could get an answer, you can say, if you just ignore all of this kind of, whatever gossip you might have heard about the speed of light being the ultimate speed of the universe anywhere else, use your understanding of Newtonian gravity and crank out the formula that tells you how big it is. So here's a picture of the sun rising, here's another picture of the sun. And so we're going to do this as a thought experiment. We're going to imagine building a kind of Lego sun. We're going to take more and more stars, we're going to bolt them together. We'll assume, instead of round star, we'll assume they're nice and square so they fit together without leaving any gaps. We'll say, how big a star would I need to build before I built a star whose gravitational field was so huge that light itself would be unable to escape its surface? And so we'll ignore the fact that when you do that, firstly you get your fingers back to good, but secondly, the star is much denser towards the centre than it is at the outside. But we can assume, for the purposes of what we're doing here, that we're going to add all of these uniform stars together, and we want to know how big it is before the escape velocity of the star reaches this number here, which is the speed of light. So Mitchell would have known the speed of light within about 5%. He would have thought it was 300,000. Well, he wouldn't have thought kilometres per second. Firstly, because he wasn't French, and secondly, because he was doing it in 1783. But roughly, he would know 186,000 miles a second would have been a number that was known. And so what we're doing is we're assuming that the density of the star is unchanged. And so this is one, the old question, which one's heavier, a ton of lead or a ton of feathers, right? And so we know that the ton of feathers fits in a bigger box, but we also know that it's the same mass. It's just that the ton of feathers is going to be less dense than the ton of lead. So he knew this, and he also knew that the density of the sun, in fact, is about 1.4 times the density of water. So the density of the sun, it turns out, is about the same as the density of honey. Roughly speaking, the density of the sun is the density of the Earth is like 5 times the density of water. The density of the sun is about 1.4. Turns out that's about the same as honey. So you can think of the sun as a giant, glowing, billion-kilometre across ball of honey, and at least in terms of its gravitational field, you're not too badly off. So what he worked out is you would need to make a sun that was about 500 suns that way, 500 suns that way, and 500 suns that way. In other words, if you took the sun and you expanded to the point where it was 500 times bigger in each direction than it is today. And this is the crucial thing. This isn't that, one day the sun's going to expand and it will engulf, Mercury and Venus, maybe the Earth will become a red giant. You've still got the same amount of sun when that happens. You've used the same stuff, you've just kind of puffed it out into a much bigger point. In this case, what we're saying is you have to actually imagine that you're joining a whole bunch of stars together they're not going to collapse, and you're going to produce an object that is actually not just larger than the sun in terms of its physical dimensions, but is also 125 million times more massive than the sun. Okay? So this was the object that he imagined existing. He had no idea what stars were. Nuclear fusion is not something that you have heard of in 1783, even if you are 100 years ahead of your time. You have to be 150 years ahead of your time to do that. So no, he didn't know why the sun shone. He didn't know what made it shine. He just assumed that you could imagine a really ginormous star. And this is the number. So once you get 125 million times bigger than the sun, that means that your radius would be about 347 million kilometres. So that's somewhere between the orbit of Mars and Jupiter, if you imagine plonking it inside of our solar system. And that thing, the surface of that imaginary star, would have an escape velocity that was equal to the speed of light. So pretend we know that a star that big would collapse, wouldn't be able to generate enough heat in its core and stop itself from collapsing. But he said, well, okay, this star would be generating light, it would be a perfectly reasonable star, but once you were a long way from it, you wouldn't be able to see it at all. In other words, the light leaving its surface would go up into the air, it would stop moving, and then it would fall back towards the star. And so he called these objects dark stars. And so it's like, it sounds like something out of science fiction. Back to the movie, science fiction movie called Dark Star, if you Google. So he had this idea that these things were possible. He certainly didn't know what we know about stellar physics, about why it is that stars shine, but everything he said here is actually pretty much reasonable. These things could exist. And he realized that these things would be invisible to observers. There's no way you can see a star whose light can't escape it. And he said, there's one way that you would be able to see this object. And the way that you would see it is by watching the effect of its gravitational field on its surroundings. And so he said, imagine if you saw a star that was doing this in the sky, and there was nothing nearby, then you would know that one of these dark stars would be somewhere in the vicinity, would be pointing up. The star was, you wouldn't see it going around in a circle, you would see it moving backwards and forwards in the sky. And in fact, how many people here have done binary star or variable star observing? Some, right? So in fact, he was the first person to work out on a purely statistical argument that when you see two stars that are close together in the sky, he realized there were more of those objects than you would expect if they were just grouped purely at random. In other words, he said that when you see a visual binary, that the odds are that, because we've only got so many stars in the sky, the odds are that they must be physically connected with each other. He didn't know anything else about their distances, he didn't know about stellar types, anything like that. But he said, the chances that we see two stars in close proximity to each other much more often than we would think, and in doing so, he is possibly the first person to apply statistics, in fact, to the field of astronomy. So statistics is a big deal, bash physics at the moment, but he was possibly a pioneer in that field. So what I'm going to show you next is actually a visualization of what we see when we look at the center of the Milky Way galaxy. And so when we look at the center of the Milky Way galaxy in regular light, we see the beautiful Milky Way. In visible light, the dust between us and the center of the Milky Way pretty much obscures everything that's going on. But if we look at the infrared, which is has a long enough wavelength to find its way through dust relatively easily, what we see close to the center of the Milky Way is this huge cluster of rapidly moving stars. And so what we see, we're taking observations in the sky, is something that looks like this. And I'm going to zoom in on one of them. This is a star that's known as S2. And it has a period that moves across the sky about 18 years. And when it's going at its maximum velocity, it's traveling at 2% of the speed of light. Here we go. It's just recently been through its moon, and it travels back down. So this is now projecting into the future. And so there's nothing we can see at the center of that orbit that would cause a whole star to move at 2% of the speed of light, walk around in an ellipse, and then have it back where it started 18 years later. So what we infer just that exactly as there's many reasons for thinking that there's a giant black hole at the centre of the Milky Way. But the motion of the stars themselves is actually pretty much something that Mitchell would have predicted. In other words, you look at these stars, you've got to get really fancy because you've got to use a big telescope, or use fancy telescopes to adaptive optics to measure the positions of these stars. But you're seeing a star moving at a velocity that would be unthinkable if it wasn't in the vicinity of something that was much, much larger than itself. Any other star moving at that velocity would just keep going in a straight line. There must be something absolutely vast in the vicinity of the star in order for it to be able to not only move that fast, but also to be forced into an ellipse rather than just taking off in a straight line. So what we deduce from looking at that, in fact, is that the centre of the Milky Way galaxy has a black hole that has a mass about 4 million times larger than the Sun. And so there's many other reasons for thinking that there's a central black hole in the Milky Way. The radio emission we see from the Milky Way, for instance, from the Sagittarius was the first hint that there was something going on here. But we found there's strong evidence for the supermassive black hole at the centre of that galaxy. So there's nothing to see there. There's nothing, you look at it and it's just this star moving in space with this dark companion. And so this isn't, what Mitchell imagined and what we're seeing in the centre of our galaxy is these two things are weirdly similar to each other. If we look at a 4 million solar mass black hole, that corresponds to the edge of the black hole, what we call the event horizon. That corresponds to, that's about a 30 million kilometre radius, I think, if I worked this out right. I can't remember whether it's a radius or diameter, I'm looking at my notes, but somewhat larger than Mercury's orbit. So if we popped it in the, I thought it was 10 million. So someone will have to work it out a little bit. But but if we plopped, if our solar system was replaced, or this black hole was in the centre of that solar system, it would be, the size of this black hole would be much smaller than the radius of the Earth's orbit. This star here, it turns out it comes within 18 light hours of whatever the central mass is, so it will be twice as far away as Pluto from the centre of the, from the central object. So while it's feeling the mass of this, while it's feeling the gravitational field of this giant black hole, and it's also coming nowhere near, in the same way that Mercury and Pluto are well separated from each other, it's nowhere near to the point where it would be at risk of falling across the event horizon, being torn apart as it comes past the sun. It's safely at some huge distance from the kind of immediate effects of the black hole, but on the other hand, its motion through space is making clear that the black hole's there. So has anyone got any kind of questions or anything at this point?
Was it made through light, or is that just like an artifact, or is that to do with light?
I think it might be your projector. I think it might be your projector. This is a simulation, I should say, because so they've taken, what they've done is if you look at the original data that they've got, it looks pretty fuzzy, and so what they've done is they've taken observations over years and years and years, worked out the orbits of these things, and then generated this as a visualization. I actually have some pictures. I was looking at pictures of the raw data, and it wasn't nearly as cool, and it didn't have the cool little speedometer thing. Possibly you could set one of them up in the centre of the galaxy and look at it and see what's going on. So no, I'm not sure what that is. So the other way that we see black holes, so the key thing about this is that it's very hard to think what else would weigh millions of solar masses, and on the other hand, fit into a space that was small enough to be contained inside of our solar system. So what else would would it be?
Well, Richard, sorry, I just thought of one thing. This star is travelling at, well, I guess you'd almost call relativistic speed. So does it have a marked precession of Perry Aster?
One thing that has been measured is you can actually see its colour change as it as a result. Notice the Doppler effect, but you can see an impact of relativistic effects as it moves. It would have to have a pretty substantial. The perihelion precession is also a function of its eccentricity, so I can't remember what it is, but yeah, it would have. There would be distinctly relativistic effects. But we've only seen a couple of orbits at this point, so whether we've measured the orbit accurately enough to see that is not clear. But yeah, any relativistic effect you can think of in the solar system, this thing has got in space, both because of the much stronger gravitational field, but also because that's a very eccentric orbit. Any other questions?
So you could assume that it doesn't have any planets around this particular star.
It's an
The
interesting.
speeds that it travels at, and
So-
the orbits.
So these are also quite early type stars, I think, from memory. I think from memory, most of the ones that we're looking at are A and B type stars. It's a very rich cluster. There's hundreds of stars within a light year of this central mass. Whereas, if you compare that to the solar neighborhood, where it's 4 light years so mostly these are fairly young, fairly bright stars. I think the thing that wouldn't. I think it could have a planet that was relatively nearby. I don't think it would lose Mercury, for instance. It's not going to be totally stripped. But I don't know, because that'd be. I have to sit down and work this out. But yeah, if Pluto was attached to it, for instance, then it would lose it on its way through there. But I think these particular stars, the question of whether or not they have planetary systems might be also a function of the environment. What's that for?
Presumably, there'd be fairly massive tidal differences between the side of the star face and the black hole and the other side.
You can work that out. I mean, it would be significantly ellipsoidal as it passes through that. In fact, I think one of the things people have looked at is whether or not you can use this mechanism to accelerate. If you have a binary star that passes close to the central black hole, whether or not you would expect that binary to